welcoming you to the webinar on quality improvement of magnesia-carbon bricks by adding nanocarbon and altering mixing regime by Achint Bishoyi, present fourth year undergrad student at the Department of Ceramic Engineering. He is the ex-secretary of NITR ICS for the academic year 2020 and 2021. Completed his internship at Tata Steel on the topic of castable refractories, and Siddharth Nanda, present fourth year undergrad student at the Department of Ceramic Engineering. He is the ex-vice chairperson for the academic year 2020 to 2021 and the present chairperson. Completed his research internship in two of the most prestigious institutes of our country, IIT Kanpur and IIT Madras. The PPT which will be presented to you was presented in CALD Conclave 2020 by our speakers Achint and Siddhartha and bagged the second runner-up position along with a cash prize of 15,000 Indian rupees. Magnesia carbon bricks. Magnesia carbon bricks were developed for the use on the hotspots of electric arc furnaces and began to be applied to converters in the late 1970s. Since they were found to have higher durability than dolomite carbon bricks, they were mainly used for converters. Then, they have significantly increased in use applications and quantities as converter refractories. Today, magnesia carbon bricks are widely applied as steel making refractories, not only for converters but also for vacuum degassers and ladles, among other equipment. Let's get into in-depth details, which will be presented by our speakers Achint and Siddhartha.
Okay, thank you, Uday. Can you stop sharing your screen so that I can upload the presentation? Okay, thank you. All right, so is the slide visible?
Yes, yes.
Okay, so to start off, Siddhartha, you can start
Yep.
with the introduction.
Okay, so hello everyone. This is Siddharth Nanda, and as the introduction is already being given by Uday, so we'll be discussing about this topic of quality improvement of magnesia carbon bricks by adding nanocarbon and altering mixing regime. And since the most of the audience are in current second years, they were very rarely know all these terms written on this. Just to give an idea, I can say, so this is as mentioned also, Uday. I just want to explain it bit more that this topic has been presented by us in the Calde Conclave, which is being organized by Calderis, which is a refractory based company. I will be talking about refractory, what it actually is and all. So this is being conducted by this is being conducted in Calde Conclave, and we got the second runner prize. Some cash prize was there. Me and Achint, both of us were there. So okay, so let's dive into it. Let's discuss about it. Okay, so Achin, can you go ahead? Yeah. So okay, so this is the first slide where you can see there is a picture. Okay, I will my presentation style is little different. I will not be going through the whatever it has been written. I will just explain things that has been mentioned here. First, you can see there is a picture on the top right corner. Okay, so this is basically a ladle. Okay, so what is a ladle? Okay, before telling all these things, let me tell you what a refractory actually is. So refractory is basically in the shape, mostly in the shape of you can say bricks, which are being used in the interior. Okay, in the interior of different iron making and steel making equipments in the industries. Okay, so you must have heard about furnaces. I guess you must have heard about blast furnace. Okay, all these things which are being used for, you can say, for the production of iron and steel. Here you can see a picture where it has been it is actually a ladle, and you can see the interior part is actually glowing. Okay, what's this is not actually glowing, this is a molten metal which is around something at a temperature greater than, you can say, 1000 1100 degrees centigrade. Okay, it's 1100 degrees centigrade. So can you even think, like, you are right now in 30 degrees centigrade, so you can think of like what would be the temperature at 1100 degrees centigrade. So at that temperature, whatever the outer material used for producing, for creating this kind of equipments will not sustain that temperature. So that's why some kind of refractory being used in order to, to prevent this molten metal to react with the equipment material. Okay, so this refractory material is being basically in the, you can say, in the interior part. Okay, it basically differentiate, it basically acts as a barrier between this molten metal, because this molten metal is highly reactive, because something at very high temperature is extremely reactive, like they can react, they can form chemical reactions whenever come in contact with any kind of metal. Okay, so these refractory material are also, okay, just yeah, these refractory metals are also used in case of in order to, sustain the temperature. Okay, now next thing is that why magnesia carbon refractories and what's the main constituents of magnesia carbon refractories. Okay, so here you can see the magnesia carbon refractories, the main components is obviously magnesia, because magnesia, it is in the form of MgO, and you can see the sources of the magnesia can be, you can say, magnesite, which is basically in the MgCO3 form. There form you can extract the magnesia. Okay, you can have fused magnesia or the seawater magnesia, because magnesium ions are basically present in the salt water in the form of magnesium, that you can extract and use as the magnesium. Now the most important point is, if there is magnesia, okay, why we need to add this kind of carbon, like what are the properties that we generally use for carbon so that it improves the characteristics of the magnesium. Okay, acha, Achint, can I share my slide? Because if I can show something, I just wanted to show something.
Yeah, yeah, sure, sure.
Okay, 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 okay. You stop, please. I will bit. Yeah. So 1 second. Can I make screen visible?
Yeah, yeah, it's
Yes,
visible.
Bhaiya.
Okay. So I just so this is the pen time opening. Okay. So just wanted to show you something. Okay, so you can see this is the magnesia. Okay, you can see large magnesia particles of some micrometer diameter length. Okay, so these are the large magnesia particles. Okay, you can say if this is the you can say some kind of ladle or furnaces, and this is the lining of the refractories. Okay, this is basically the lining of the refractory. Then this refractory is basically prepared by some kind of magnesia, and you can see this is initially, this, if only magnesia is present, it is basically magnesia refractory. Now what we are doing, we basically adding carbon. Okay, as you can see in the PPT only, it has been mentioned where it is. Array, why cannot I? Okay, so you can see what are the improved characteristics by adding carbon. First, it is non-weighting. Carbon is hydrophobic in nature. Okay, so it doesn't love water, so it is non-weighting characteristics. Second is corrosion resistance, and third is increasing thermal shock resistance. So right now I'm just pointing out few things. Now, as I said, these are the magnesia particles are there. Now carbons are basically small particles which are basically present in these small gaps. Okay, in these small gaps, basically carbons are present. Okay, these are basically small gaps in which carbons are present. So what happens that the molten metal that is present inside the furnace or ladle, which are very much highly reactive, if they find any kind of gap between these refractories, they will try to penetrate. Okay, they will try to penetrate into it. Okay, they will try to penetrate into it. So if there is no carbon is present, then between the gaps between the different magnesia particles, the molten metal can penetrate, and they can basically corrode. Okay, they basically react with the refractory material, and they can corrode the refractory from the inside. Okay, which is a very hazardous situation for for the production. Okay, so what happens that when the carbons are present, they basically fill up the gaps. Okay, they basically fill up the gaps, so it reduces the corrosion, or you can say improve the corrosion resistance. Okay, as it has been mentioned here, the second point is the thermal shock resistance increases the resistance to thermal shock. Why? Because carbons are highly thermally conductive. So what happens when thermal conductive? As you can see, the inside temperature of the molten metal is something around 1100 degrees centigrade or above. The outside is something around 30 degrees centigrade or above, 30 degrees centigrade. So if it is very low thermal conductivity of these material, then it will not let the heat pass through the refractories. Okay, so in that case, what will happen if the thermal conductivity is very low? There's a huge gradient. There'll be, because this is at very high temperature, this is at very low temperature, so there'll be a thermal gradient developed, and because of that there'll be a strain. There'll be a strain developed. There will be thermal strain developed, which will result in some kind of crack, which will basically result in some kind of crack. Okay, so the thermal shock resistance is increased if you increase the thermal conductivity. If your thermal conductivity is increased and it lets some heat pass through the refractory, then the temperature difference will be low, the thermal gradient will be low, the thermal strain will be low. Also, carbon has low thermal expansion. Why low? What is this? What will happen if you have low thermal expansion? If, let's say, two particles are there. Okay, so when you heat, the tendency is of the material is that it will expand. So now you have a limited volume. Okay, so in from here, when you are heating, what will happen? The particles, the total volume will be same, but the particle size will increase. So they will basically increase the stress. They will apply a load on each other because the volume is same, the particle size is increasing, so there will be a development of stress, and that will result in the crack. So this is called as thermal shock. So by using carbon, you can reduce the thermal shock resistance. Okay, so these are the benefits of using carbon. Next is antioxidants. Why we generally add antioxidants is that we all know that when this is basically carbon, so this carbon is basically in the solid form. Okay, these are basically solid form. When it finds oxygen, oxygen can be from this, if this is the you can say lateral furnaces, the oxygen, this is outside, it can directly react with the oxygen from the top or from the oxygen present in the slag. If it reacts with the oxygen, which is basically the gas form, it will become CO or CO2, and this will just in the form of gas. The carbon present in the solid will be evaporated out in the form of gas. So as a result, what will happen? This will create pores, because this carbon solid will go into gas as CO2, and what will CO2 or CO, what will be left behind? It's just pores, or you can see just voids through which this slag or molten material can penetrate and corrode the material. Okay, so that is why you can say antioxidants are used. Antioxidants can be aluminium, some kind of metal. It can be B4C. It can be B4C. That things will be discussed a bit later by Achint, that regarding the antioxidants and all. But for time being, you can understand, if you are using some kind of metals which have higher tendency towards oxidation than carbon, that is, if oxygen is present and aluminium is present and carbon is also present, then aluminium will react with the O2. This will form this aluminum oxide Al2O3, and it will prevent the carbon from oxidation. So the carbon will remain in the solid form and it will be like there without evaporating out. And this aluminum oxide would basically coat the carbon. It will basically coat the carbon particle. So what will happen? It will prevent it from the oxidation. That is why it is called as antioxidants. Antioxidants for the carbon, that is, it does not allow the carbon to oxidize. And next you can see is the binder, or you can say resin. What happens, the binder is because basically binder can be of organic binders are present, phenol, resins, all these kind of binders are present. Why binders are basically added? Because as we know that, like, carbon is there, magnesia is there, also you have some kind of antioxidant. You need someone who will bind all these things together. So when phenol or resins are present or binders are present, when you temper it up, temper means you are heating it about 200 degrees centigrade, so they will basically form some kind of interlocking structure. Okay, some kind of network or interlocking structure where these small particles are permanently fixed in their position. It basically do the thing of holding all the particles together, all the components together. Okay, so these are different constituents of the magnesia carbon particles. Okay, so next, this is the thing that I wanted to show. Okay, next is the inherent problems with carbon. What happens in the carbon is that carbon oxidation, as I told, that when this is, you can see here there are lots of voids are present. Initially there was no voids because there was carbon present, but when this carbon reacts with the oxygen, so they will basically oxidize and create pores. Even if you are using antioxidants, still if you increase the carbon weight percent to certain limit, then antioxidants will also cannot be able to prevent the oxidation, and this will create this porous structure which will result in, you can say, result in the corrosion. Okay, because there are voids and slag and all can pass through it. Next is in case of direct oxidation of carbon. Okay, also when carbon is getting oxidized, it is evaporating out as in carbon monoxide or CO gas, right? And CO gas is a harmful gas. You all know about this. CO gas is a harmful gas. Okay, so this is also another demerit. Why, if carbon is used in an extreme or if more weight percent, then there is possibility of carbon pickup by molten metal, because for steel production you require less carbon percentage is required, less than 4% or 3% carbon is basically required for steel production. But if you are using more amount of carbon in the refractory, what happens is that the molten metal present in the blast furnace, they pick up carbon, as a result of which the molten means the melt carbon that is coming out, it will have higher carbon percentage, so the steel quality will be poor. Okay, okay, next. Okay, so that is why, now that we know that if you are using simple magnesia, then there are some properties, but if you are adding carbon, then the properties are increased, because carbon can fix in between the magnesia particles. But if you are increasing the carbon particles further, carbon amount further, there is also the problem of oxidation and other problems. So that is why we think that what we should use now, carbon is basically conventionally the source for carbon is graphite. Okay, and the graphite is basically used for the source of carbon. Now we think that what source of other carbons that we can use which can overcome such issues. And in that case we have gone through a lot of literatures, and we found out that if we are using nanocarbons are also the source of carbon. Okay, different another source of carbon, which is basically carbon particles with in the range of 100 nanometer. The radius is basically very small, range is basically 100 nanometers. And in the further coming slide, we have discussed, basically Achint will discuss what are the properties improved by using these nanocarbons. Another thing that I have mentioned here is relative volume of the atoms in the grain boundaries enhances. So now when you are using small particles, okay, So what happens if we just show this thing that you are using basically the grain boundaries. When you are using small particles, the grain boundaries is what? The grains, the boundaries in the grain, these are grains. Then the grain boundaries, the overall grain boundaries, by reducing the small size, the grain boundaries increases. Okay, the grain boundaries increases, so that when the crack propagates or the slag, okay, this is because like the slag is going into it. Okay, the slag is going into it, and if there is a simple road like this, the slag can go directly pass through it. Now what happens when you are having small particles? The slag will go and it will inhibited, it will be struck, because it is going like this, then it has to change its direction, it has to change its direction. So the slag propagation is basically decreases. Okay, and also because of the small size, because of the small particle size, the total surface energy also increases. And what are the properties developed, that will be discussed by Achint. So Achint, over to you.
Thank you, Siddhartha. Siddharth, can you stop
Yeah.
sharing so that I can share my slide?
Yes.
Thank you. Just a second. Yeah, so I think the slides are visible now.
Yes.
All right. So, as discussed by Siddharth, we have a limitation in the amount of carbon that we use. So, what was done was we introduced the nanocarbon was introduced. So, by introducing nanocarbon, these are some of the basic properties that are taken as a conclusive result. Maybe the third years can relate to it after they have, because they have studied process ceramics and may be knowing about this term. But for the second year, I'll just explain the properties in brief, and then I will say what all what kind of improvement we got. So AP is apparent porosity. Porosity, as you know, is how much amount of air or void that is present in a material. It is fairly simple to calculate. There are two methods. You can use a boiling method, in which you just put the sample in water and then bring it to a boil till 30 minutes or so, so that all the remaining air from the voids of the materials are removed. I mean, of course, it doesn't remove the voids that are present inside the material, but mostly the surface pores and some of the pores which are accessible through the surface. We can know the porosity. That's why it's called apparent porosity, not the true porosity. So when the test sample that contained around 0.9% nanocarbon and 3% carbon from graphite. Graphite is used as a source of carbon in refractories because the oxidation temperature of graphite is higher than just simple carbon from other sources. If you can if you study a bit more, you can see that carbon oxidizes somewhere around 250 to 300 degrees Celsius in normal conditions. But carbon that is sourced from graphite, it oxidizes from 350 to 450 degrees Celsius, which is advantageous in refractory application. Graphite, 3% carbon from graphite, AP was 4.7 weight percent. But when 0.9 weight percent carbon, nanocarbon was introduced, the value of AP decreased to 4.3%. So definitely the packing was much better. Now, where the AP value for the conventional brick is much lower and have it is 3.3% because conventionally when the graphite is used for refractory manufacturing of the magnesia carbon refractories, 10% graphite is used. So which is much higher than what the test sample contained. Now coming to the next one, BD. BD is bulk density. Um, Density is mass per unit volume, but when we calculate bulk density, it means the density including the pores. So the BD for conventional brick, which is used in the refractory application, is 3.05 gram per centimeter cube. CC is for centimeter cube, and the samples that we got the data of had a value of 3.12 gram per cc, which is much higher because the pore filling was better due to the nanocarbons. Now, CCS is cold crushing strength, and as the name suggests, it is the strength of the material at ambient temperatures. That's why it's called crushing strength. Crushing strength implies that that load at which the failure of the refractory occurs when the load is applied on a flat surface and the unit is kilogram per centimeter square. The conventional brick had CCS of 375 gram, 375 kg per centimeter square, and the test sample containing nanocarbon had a CCS as 510 kilogram per centimeter square. So if you imagine 1 centimeter square, that is 1 centimeter by 1 centimeter surface, 510 kg. If you can imagine, it's like a lot. So when in actual application the bricks are used, they are in the dimensions of say around 100 millimeter by 120 millimeter. So a lot of load can be accommodated by a single brick, and there is a continuous structure of the bricks. So that's why they are very structurally strong. But yeah, this is for the ambient temperatures only. The strength drastically decreases when the material is subjected to high temperatures. So with that comes the next property, which is HMOR, which stands for hot modulus of rupture. Hot implies that the strength is measured when the sample is very hot, and when I say very hot, it is 1650 degrees Celsius, in which it is soaked for around 30 minutes, then the testing occurs. And for your reference, iron melts at 1538 degrees Celsius and aluminum melts at 660, around 700 degrees Celsius. And if you take steel, it will melt around 1600 degrees Celsius. So you can imagine the temperature at which these materials are being tested uh, are the temperatures where most of the metals they melt. They do not have any form at the temperature, and we are testing the strength of these materials at that temperature. So modulus of rupture means failure, of course. So this is little different than CCS. In CCS, we apply load to a specific area. In HMOR, the load is applied to a point. So HMOR is a 3-point test. 3-point test means the support is given at 2 points and the load is given on the third point, which is in the middle from the opposite direction. So imagine breaking a stick with your hands, in which you hold the stick from two sides. When you use two hands, of course, you hold the stick from two sides, and using the thumb or just by bending, you break it. So it breaks from the middle. It is similar to that. So when the sample was tested with only 3% graphite and no nanocarbon, the HMOR came as 25 kg per centimeter square, and when the test sample containing 0.9% nanocarbon, uh, it was it was used the HMOR came as 45 kg per centimeter square. So we are seeing that the properties are increasing. The main properties, that is CCS and HMOR, they have increased almost twofold by introducing nanocarbon. Um, Now, in this image that you see in the bottom right corner, it is a circular sample in which you can see some yellowish kind of stuff on the outer ring and grayish black stuff towards the inside. So that grayish black stuff is the mark of carbon content, and magnesia looks like that normally. That yellowish stuff is magnesia. This is one of the methods to test the oxidation resistance. Uh, so what we do is we cut a cylindrical sample of normally 40 millimeter diameter and same height, 40 millimeter height, and then it is put in the furnace in which it is subjected to the application temperature, which is mostly around the melting temperature of iron, that is 1500 to 1600 degrees Celsius, for 1 to 2 hours, based depending on uh, the actual application area. Like for ladles, it is different. For electric arc furnaces, it's different. For tundish and everything, all are different. So after a while, the sample is taken out and a cross section is cut, and the diameter is measured up to how much extent the carbon is remaining. So then it is compared with the total diameter of the cylinder, that is 40 millimeter. So we get a percentage of how much oxidation has occurred. So when we see here, when we use only 3% graphite with no nanocarbon, there was 25.56% oxidation. And when the nanocarbon was used, there was only 21.82% oxidation. Now you have to bear in mind that when it comes to oxidation of the material, even 1% of improvement matters a lot, because what we are talking about is our huge, very huge equipments, and um, say even if there is a 1% more oxidation, the structure may collapse because the carbon after oxidation leaves voids in the magnesia which has had formed the matrix, and of course the application zone has slag which sticks to the magnesia, and it enters and penetrates and it damages the structure, and hence it will result in the collapse of the structure. So these are some of the properties which are which we can by which we can determine that actually if we are seeing an improvement or not. These are some of the preliminary testing, and there are many more testing methods by which we can confirm, but that may be a little out of the scope for this topic and this webinar. So moving forward, let's see what are some of the other factors that may be affecting the quality. So you know, the higher the graphite content, the higher the orientation dependence of thermomechanical properties. Uh, you can see the structure of graphite here. Graphite is layer. It is formed by layers. So you know that graphite is used as a lubricant because its molecules have the ability to slide over one another. So when the graphite grains are larger, um, the orientation of these molecules have a large effect on the thermomechanical properties. In the magnesia carbon brick, the major antioxidants that are used are aluminum powder, which was explained by Siddharth, and also we can use boron, a composite of boron and carbon. So when the carbon is interacting with the aluminum, it forms Al4C3, which at temperatures greater than 750 degrees Celsius. Then, when the temperature increases from 1100 degrees Celsius, Al4C3 forms Al2O3. This reaction was explained by Siddharth, and and finally, when the temperature even further increases to 1400 degrees Celsius, due to the presence of magnesia in the matrix, magnesia and alumina form spinel. Now, what is spinel? You will get to know when you study your further courses in ceramics. Just so you know, spinel is a very important material. It's the name of a structure, but it is used interchangeably with spinel with this material, mag-Al spinel. We call it mag-Al spinel, magnesia and alumina spinel. So when the spinel formation occurs, it results in the volume expansion. So the AP, apparent porosity, uh, decreases, and hence BD increases, which also increases certain other properties like thermal conductivity also increases because porosity decreases the thermal conductivity, as you can guess, due to the presence of air, which is a bad conductor of heat. So this also further helps in oxidation reduction, and the corrosion resistance also increases. Now, since I have mentioned corrosion resistance, you must know that where magnesia carbon bricks are used, the environment is mostly slag, and slag is very corrosive. That's why magnesia carbon bricks are used. Otherwise, only in the metal zone, that means the part where only the metal is in contact with magnesia, carbon is not required much. But in the slag zone, the carbon is required because carbon has a non-wetting property which does not let the slag stick to the magnesia and corrode the surface. Mm, and as an antioxidant, B4C can perform much better than Al aluminium powder, because B4C reacts with the carbon monoxide, which forms in the process of oxidation of carbon. And this reaction occurs at very low temperature. So before before the carbon actually starts to oxidize, before C can prevent the oxidation. So that's why before C also can be used, but due to the cost factor and procurement of materials, aluminum powder is mostly used. Now let's move on to the next. Yeah. So after introducing this nanocarbon into the fine fractions of the refractory, it was further realized that we need some more improvement in the properties also. So we thought that it was thought that what if we change the mixing route? It is not like you just put all the materials together and mix it for some time and it's done. The packing of the materials, the grains in the structure, it depends a lot on how you mix it. If you over mix it, then the segregation of of the different aggregates that will be formed, and the packing will not be proper. This you will learn, the second years you will learn it in process ceramics, which will be taught by Bhattacharya sir. So I would suggest you pay special attention to it, because a lot of concepts will be cleared in that. Now coming back to the topic, a composition containing approximately 1% nanocarbon was processed in three different routes. In route 1, the nanocarbon was added with coarse magnesia grains, whereas nanocarbon was added with other fines in route 2 and 3. When the three different routes of mixing was compared, route 1 showed better density and higher strength values than the other two routes. Why this happened is because the mixing of nanocarbon and magnesia was better when it is in mechanical stirring, means mixing in dry and hot condition with coarser magnesia fraction. So the dispersion of nanocarbon is better, and magnesia grains are well coated with fine nanocarbon through route 1. In other routes, when the nanocarbon was added with the fine particles, the coating of nanocarbon was not that effective, because the other material, that is graphite, was in higher concentration than the nanocarbon. So some of the grains of magnesia were coated with nanocarbon and some were coated with graphite. That's why there was a discrepancy in the properties that was obtained. Also, if you see, if you also, I mean, there will also be a subject taught by Professor Arun Chaudhary. In that, you can know that agglomeration will occur when you mix too much of fine fractions at a time. That means the actually, yeah, this will also be taught in Professor Bhattacharya's class. So again, process ceramics. Mm, Okay, coming back now, agglomeration will occur when you mix too much of fine fractions because the fines they will attract with each other and they will form bigger particles and hence the packing will not be proper. Mm, Okay, now because of the agglomeration tendency of fines, the nanocarbon added are not dispersed properly. Also, the finer nanocarbon particles are much more reactive and when they are properly distributed with the magnesia, the ceramic phase like spinel and aluminum carbide in the presence of the aluminum powder as antioxidant will be much better. So here, from here, what we can conclude that not only does the properties improve, but also the total carbon content was made lesser than what was required. Further, change in the order of adding individual components during mixing also improved certain properties. There are different sources of nanocarbon like graphene oxide nanosheet, carbon nanotubes, and nanocarbon black, which are available in the market. And if we use them, surely enough, there will be a considerable improvement in quality of the bricks which we hope will result in its better life, service life, and performance. So this is not our original work. Most of the work was performed in our department only under Professor Ritvik Sarkar, and we got in contact with him and we asked whether we can draw some conclusive mm, like a review paper from his workings, and he agreed. And we also referred to some other research papers, and we combined both of a lot of them, and then we came to the conclusion that we presented before you. And you can see the some of the references that we used to prepare this presentation. So this presentation, although we have presented once, but we thought that in simple terms, it would be a good way to introduce you to ceramics because you are just delving into the main subject, and I don't think I don't know about other fields, but I feel that refractories are like bread and butter for ceramics because uh, see around you, even if you don't realize, most of the things that you use have an application of ceramics in them because you prepare any metal, you need ceramics. You use furnaces to make glass, to heat the whiteware and everything, you need refractory. So whenever you need some protective layer in for from heat, you will need refractory. So if you know refractory, you will know most of the properties that is used in other ceramics. But yeah, other ceramics are also very important, and I would suggest you pay special attention to studies when whiteware and glass comes because those are some little complicated things. Siddharth can shed more light on that because he's the expert. My field is refractory, so if there are any questions, please shoot away. And I can see there are no questions in the chat box. So whoever has any doubts or any queries, please raise your hands and speak up.
Thank you, Siddharth Bhaiya and Achin Bhaiya, for sharing your knowledge with all of us. Guys, if you have any queries, please raise your hands. We will pick up and your queries will be solved by Achin Bhaiya and Siddharth Bhaiya.
You can also write down in the comment section, sorry, in the message section also. If you have any doubts, we can wait for 1 2 minutes. And please open, like, you must have something, because lots of terms are being used. You might not have heard about these terms. So I guess there is also no third years present, because if they are present, they must have some kind of doubts. Because okay, but if you have any kind of doubts, you can go ahead, please. If you have, if you have paid attention, you must have something to ask. No doubt.
Excuse me, Bhaiya.
Yep.
I myself have a doubt.
Okay.
Actually, comparing comparing the sizes of both magnesia and carbon particles, what should be the ratio, the range of ratio which will suit perfectly for building a good quality refractory? Is there any specific range?
Siddharth, let me take this question.
Yep.
Mm, so, have you heard about packing fraction? You must have read in process ceramics.
Ha, Bhaiya.
So, there were some equations you must have heard about. Anderson equation. You must have heard about Dinger-Funk equation.
Ha, Bhaiya.
So, when you make any refractory, we don't use just means we first decide. Let me explain you how a new kind of new refractory is made. First of all, the properties that is required in the refractories are decided. Then the materials that fulfill those properties are taken. Like we need good resistance against alkali environment, we take magnesia. We need good resistance against slag corrosion, we take carbon. Okay. Now after that, we decide that in which form we need this material. So best property of carbon is got in graphite. So take carbon from graphite, and you cannot take bigger grains of graphite. So we take graphite in fine fraction. Fine fraction is mostly below 325 mesh. And if I remember correctly, which I don't remember, I know 325 mesh size. I don't remember. Let me just look it up. And another thing, when you talk about manufacturing in refractories, nanometer, these terms are not mostly used. Sizes are mostly referred in mesh sizes, which, if I remember correctly, Arun sir must have taken a lab in which this sieve analysis was done. Am I correct?
Ha, Bhaiya.
So in sieve analysis, you must have used the mesh sizes. So 325 mesh is 44 microns. So anything lower than 325 mesh or 44 microns micrometer is taken as fines. Now for the aggregate will form the matrix of the refractory. So we take magnesia. Now magnesia is taken in various other forms. So there are different sizes of the magnesia. It is taken from 6 to 10 mesh, then 10 to 28, 28 to 44. So there are different ranges of sizes. We don't have a particular size because a lot of materials are there, and some plus minus means there is a level of tolerance. So that's why a range of particles is taken. Now here comes the Anderson equation or Dinger-Funk equation. Mm, Dinger-Funk equation is used mainly when castables are made, because in castables packing is of more importance than in these formed refractories. So Anderson equation is the standard. You use Anderson equation, you put the Q value. Q value is mostly 0.2 to 0.3 in refractories, and then you will get in which size, how much amount of materials you will be using. It is means it will just like work like magic. You don't have to do anything. Just put the values in the equation, and you will get how much how much of a particular size. you have to put so that you get the maximum fraction. And this maximum fraction you will get after proper mixing. If you mix it for less time, you won't get proper fraction, proper packing. Then if you mix it for more time, then also you will not get proper packing. So, deciding the amount of aggregates in a particular size fraction, you will get it from Andreessen and Dingerfunk equation. Actually, Dingerfunk equation is more better because there is a limitation which Bhattacharya sir must have highlighted that the Anderson equation also gives you some amount of materials at zero particle size. And when the amount is zero, the particle size is in negative. So Dingerfunk equation is better. But the implementation of Dingerfunk equation is a bit complicated. That's why Anderson is mostly used. Did I take your question properly or did you want to ask anything else?
I'm fine. Thank you, Baya. I have understood.
All right. So anyone else? Anything? Any more questions?
I guess there is no questions. Uh, Okay, so I guess we'll be concluding. Just for the information that at the end Uday will be saying about that, but I just wanted to say one thing that these things will be taught in future. And being in the ceramic department, since you are in the third year, so you can explore these fields. And there are three basically main industries where the ceramic technologist or ceramic engineers are required. In that case, refractory is one of them. Okay, there are lots of companies who come for recruiting. Refractory is one. Another, you can say, whiteware. And refractory will be taught by Ritvik Sarkar sir, and for duals it will be taught by Devasish Sarkar sir in your 7th semester. And whiteware it will be taught by your Bhattacharya sir. And it is another industry is glass. For lots of companies will be coming for glass also, and it will be taught by Palza. And also you can you must be focus on cement. The cement industries also come. So all these things are very important. These are main industries where you can target. So yeah, so refractories, I guess you must have got some kind of idea. And okay, so if you if you have any questions, so you can either post in the WhatsApp group also, or you can personally message Achint and me. I guess you might have our number. Okay, so Uday, you can conclude it, I guess, and conclude the meeting.
Uday, before concluding, I just want to say a few words. Uh, the juniors who haven't yet started the refractories, I would suggest you take up the PDF of refractory technology by Ritvik Sarkar sir. You know, he will be teaching you the same subject, and you just read the first four chapters. Okay, there he has covered the introduction, types of refractories, and some of the properties and testing methods. Okay, that will be most helpful for you when you will be studying refractories, because what sir will teach, it will be mostly from that book itself. And the first half of the subject will be about till the properties only. After that, when he will start teaching the different types of refractories, then the different properties of materials that will be discussed. But these first four chapters will be common. And everything the mainly the testing methods, they are very simple. You just have to imagine how they are being done, and you can find the videos of each and every testing on YouTube. You just have to search it. So you can download the PDF of that book, Refractory Technology by Ritvik Sarkar sir, CRC Press.
Thank you, Siddharth Bhaiya and Achin Bhaiya. Thank you guys for attending this session and making it a success. Hope you all have gained enough knowledge and you have got some idea about the refractories. Hope you use this knowledge in your future. Uh, you know, you can ask your queries anytime. You can message the speakers. and hope you all are doing well in this COVID situation. Thank you, guys.
Thank
Thank
you,
you.
everyone. Yep.
Thank you so much, NITR for having me again in this platform.
Welcome, Achint. Okay, guys. So we are leaving. Thank you.